Okay, this is section 3.1, page 14. So in this section, describing, exploring, and comparing data. That's chapter 3. 3.1 talks about measures of center. That's crucial for what we do. Definition: measure of center is a value at the center or middle of the data set. And we have 3 of those that we focus on. The 3 most widely used measures of centers are the mean, median, and mode. We're going to get those out of the way. The mean, which is the arithmetic average that you know of a data set, is computed by adding, oh, that's too thick, by adding all of the values of the variables in the data set and dividing by the number of observations. So, the population arithmetic mean is denoted by mu. Is computed using all of the individuals in a population. The population mean is a parameter. And you find it by taking the sum of all the measurements divided by n. Capital N stands for the population, the total population. Little n stands for the sample. The sample arithmetic mean, we denote that by x bar. X bar indicate that this is a sample. Is computed by using some of the individuals, not all of them, in the population. The sample mean is a statistic. And you sum up all the data in the sample divided by the sample size. Population size, sample size. So when I look at the next problem, of the 42 students enrolled in an introductory statistics course, the data below are the first 10 exam scores. Treat the 10 students as a sample of the population, which is the whole class, in this case 42 students, which means we're gonna use x bar. And here are their scores. So we're gonna do this on a calculator. We take x bar, we say that's the sum of all the scores. In this case there's 10 of them, and that would be the 82 plus 77 plus 90 plus 71 plus 62, 68, 74, 84, 94, 88, and divided by 10, make a count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. You plug this in a calculator, that turns out to be 790 divided by 10. That turns out to be 79. The sample mean, or the sample average, for those 10 scores is 79%. So note here, capital N is 42, and the sample, so this is the population, sample is 10. We're going to come back to this problem and do a bit more to it. For now, that's the arithmetic mean, which is the mean. Now, when we talk about the median of the data set, is the value that lies exactly in the middle of the data when arranged in ascending. Ascending means from lowest to highest. We use M to represent the median. Different books use different notations. So there are 2 options. Either we have an odd number of data set, like, or even. In this case, the previous problem, we had 10 students. That's even. So arrange the data in ascending order. That means from lowest to highest. The median will be the middle if you have an odd number. Look at these numbers right there. They are in order. 2 below, 2 above. The median is the number in the middle. So when you give me the median, if I take the median and I count the numbers of the scores above and the scores below should match. If I have an even number, we have a problem, because if you say, look, there is no middle number. Arrange the data in ascending order still. The median will be the mean of the middle numbers, the mean of those. So the median would be, the mean means the average of the two. That would be a 23. Notice 23 is a number right there. Below are 3 scores, above are 3 scores. So the median will always break the data into 2 equal parts. Take the median, look above it and below it, the number of scores will match. Mid-range. The mid-range of a data set is the value midway between the minimum and the maximum value. The mid-range is the lowest value plus the largest value divided by 2. Now, use the data from the introductory statistic example from above to find the median. Well, let's see. If I look at that data set, if I want to arrange those, I would arrange, let's see, 82, 77, 90, 71, 62, 68, 74, 84, 94, and 88. If I take this data and put it right there, this is the best way to organize data. Stem and leaf are really useful. So if I put those in order now, I could arrange them easily. 62, 68, 71, 74, 77, 82, 84, 88, 90, and 94. 10 of them. There we go. Now, there's 10 of them, so if I want to find the median, that's going to be the middle. Well, let's see. If I take 10 divided by 2, that's 5. 1, 2, 3, 4. The fifth, and 1, 2, 3, 4. I'll take the middle 2 because that's even. And if I put this in my calculator, I'll get 79.5. Again, pay attention to 79.5 is a number that's right there. Notice there are 5 below it and 5 above it. That's the median. The mid-range. If I want to find the mid-range, so there's the median. I'll take the lowest number plus the largest number divided by 2, and the mid-range would be a 78. Now, rounding off, carry one more, so this is in general how we're going to do this. Carry one more decimal place than is present in the original set of values. So anytime you have a set of values, if they're integers, carry one decimal beyond if you have decimals. If it's one decimal, carry 2, and so on and so forth. Let me enlarge this a bit so we could write on it. Here we go. Now, the third value that we wanted to discuss was the mode. The mode of a variable is the most frequently observation of the variable that occurs in the dataset, meaning the most repeated. If no observation occurs more than once, we say the data have no mode. So remember, it must repeat for it to have a mode. If the dataset has more than one observation that repeats the same number of times, we consider multi, meaning many, module. Multi-model. Alright. Oh, come on. There we go. Now, following three examples. Find the mode for each example. The following data represent the number of O-ring failures on the shuttle Columbia for its 17th flight prior to its fatal flight. Well, do you see that 0 repeats the most? That would be the mode. How about here? The data set test scores from above. We have 82, 77, 90. Well, it seems nothing repeats. There is no mode. And hair color of 10 people, brown, 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 brown. So brown has 4. Blonde, 1, 2, 3, 4. Red has 2. So wouldn't you say the mode would be brown and blonde? Now, sometimes we have a table with a frequency. That is, the following table gives the height of a sample of 100 babies. It's very hard to list 100 babies. Instead of looking for the specific height, you start giving an interval. You say how many babies, who's between 3 and 4.9 pounds, right? How many babies weigh between 5? Well, 5 babies weigh between 3 and 4.9 pounds. Between 5 and 6.9, 32. Between 7 and 8.9, 40. 18 between 10 and 10.9, and 5 between 11 and 12.9. So, we want to find the mean for those 100 babies. We're going to get a number, and of course it's not going to be exact, but it's going to be a good estimate. So, class midpoint, you know how to find the class midpoint. Add the 2 divided by 2. That is 33.95. Class midpoint, 5 plus 6.9. You know what? I need a thinner. There we go. Now it's going to look better. 5 plus 6.9 divided by 2. And this is going to be 5.95. And 7 plus 8.9 divided by 2. This is going to be 7.95. And 9 plus 10.9 divided by 2, 9.95. And 11 plus 12.9 divided by 2, this is going to be 11.95. Now this says multiply the frequency times the midpoint. So since we don't know how many people weigh 3, 3.1, 3.2, we take the average of this multiplied by the 5, the average of this multiplied by 32, and the average, and we say that's about the total. So we take 5 times 3.95. We take 32 times 5.95. We take 40 times 7.95. We take 18 times 9.95. And we take 5 times 11.95. Now, if I add those frequencies, they add up to the total of 100. And if I add these numbers, put them in a calculator and add them all, I get 767. And let me see if this calculator, it's been giving me a hard time to work. Here we go. So if I go by and I take 5 times, okay, it's not working. I don't know what's wrong with that. I gotta fix that up. So I'll use the other calculator. But this one takes the whole screen. This one I'm gonna save until we do heavy work. Let me see if I could shrink it. That's the calculator. That's the same calculator you're gonna get from the library. Okay, I can't seem to shrink the page. Oh boy. Okay, the whole thing shrinks. Let me shrink this one too. So there, I'll take 5 times 3.95 plus 32 times 5.95 plus, oh, you're not seeing this. Let me show you this. There. I can't expand this. Oh, wait. I thought it would expand. It doesn't. Okay. Plus, I could take, oh, unless I shrink it more. So you can see it all. There, much better. So where are we? 5.9 plus 40 times 7.95 plus 18 times 9.95 plus 5 times 11.95. Now, unless I made a mistake, 760. There you go. And now, obviously, I'm going to take this and say, okay, now what? Find the sample mean, and according to the formula, the sample mean, you take this product and you divide it by n. So you take 767, and since it's 100, it's easy. You say the sample mean is 767 divided by 100, which is 7.67 pounds. That's the average for those 100, about. Now, resistance statistics. A numerical summary of data is said to be resistant if extreme values, very large values, or very small values relative to the data do not affect it substantially. Meaning, the following are wait times in minutes in a dentist office. You go to a dentist office, and this is the following. People wait 1 minute, 1 minute, 2 people waited 2 minutes, 3 minutes, and 5 minutes. Find the mean and the median. The mean. If I want to find the mean is 1 plus 1 plus 2 plus 2 plus 3 plus 5 divided by 1, 2, 3, 4, 5, 6. I'll get 5, 10, 12, 14 divided by 6. 2.3 minutes. That's the average wait time. If I want the median, well, there's 6 divided by 2 is 3. So I'm going to take the average of those. Median would be 2 plus 2 divided by 2, which is 2 in this case. Note that the value of 102 minutes added to the data. Now, instead of 5, 6, it's 7. The 7th patient came in and waited 102 minutes. Find the mean and the median. Well, now the mean is 1 plus 1 plus 2 plus 2 plus 3 plus 5 plus 102 divided by 6. That turns out to be 16.6 minutes. Notice the average went up from 2.3 minutes to 16.6 minutes. So this one extreme value affected the mean versus the median. 1, 2, 3, 4, 5, 6, 7. So if I look at the bottom 3 and the top 3, the median is a 2. Notice it didn't get affected. So the median is resistant. And mean is not resistant. All right. One more thing to discuss. We need an easy way of figuring out how is the distribution skewed left or right. And there is an easy way of figuring that out. And I'm going to show you how to do that really quick. So we take the median. The median is halfway through the data. About halfway through. And it turns out skewed left follows the mean. If the mean is less than the median, then the distribution is skewed left. If the mean is equal to the median, roughly, then we say it's symmetric. The left and the right look very much the same. And if the mean, if the mean is bigger than the median, then we say it's skewed right. So here we want the mean to be somewhere to the right, and here we want the mean to be somewhere to the left, and here we want the mean to be very close. So, general rule, if the data are symmetric, right, we use the mean as a best measure of center. If the data is skewed left or skewed right, we use the median. So you look at the distribution. If it looks symmetric, use the mean. But if it looks like it's skewed left or right, then use the median because it's not affected by those great or big scores. Now, FISCO scores range from 300 to 850, with a higher score indicating more credit-worthy individuals. This is the actual credit score in this country. The distribution of the FISCO score is skewed to the left, with a mean of 723. Do you think the mean FISCO scores is greater than, less than, or equal to 723? I think the mean, it's a skewed to the left. The mean is less than 723 because it pulls towards the tail. In our case, we just said if it's skewed to the left, the mean is less than. If it's skewed to the right, the mean is greater than. Since the mean is 723 and it's skewed to the left, the mean is going to be less than the median. What proportion of individuals have a FISCO score greater than 723? 50%. Remember, the median cuts the population exactly in half. And last problem we have, match the histogram shown to the appropriate symmetric statistics by writing the appropriate numbers in each histogram. Okay, let's see. So they're trying to tell us, look at those and tell which is which. Well, this looks symmetric except for that part. So which of those look close? I'm going to say this is a 1 or a 4. I'm going to say a 4 because if it's equal, that shouldn't be bigger than that. So 4, it's a bit skewed to the right. And I notice this is symmetric as well, except for that part. So I'm going to say this is a 1 or a 4. And again, I'm going to say a 4 because this means they're exactly the same. This means they're altered somewhat. On this problem, I noticed the highest are toward the left. So it looks like the mean, so this is skewed to the left. The mean should be, this is skewed to the right. The mean should be bigger than the median, right? So the majority of the data is to the right. If you really draw the scale, you could see that it's extending to the right. Well, which of those has the mean bigger than the median? This must be number 2. And here, I noticed that the mean is going to be more toward the left because the median is, because the data is skewed to the left. Look, if you connect those buildings, do you see the majority of the measurements are to the left? So this is skewed to the left. I should write that down. Which means the mean should be less than the median. This is skewed right. So which of those has the mean being less than? That must be number 2. and the other two are symmetric. And that's pretty much it for this section.